Welcome to Submodule 3 of 3 in our Introduction to Torque and Drag series. In this session, we shift from theory to practice, focusing on monitoring, management, and optimization techniques that enable us to effectively control torque and drag in drilling operations. In this final submodule on torque and drag, our focus shifts toward practical applications, specifically monitoring, managing, and reducing torque and drag during drilling operations. By the end of this session, you should be able to, first, explain how torque and drag are monitored in the field. This includes understanding which parameters must be measured, such as pickup and slack-off weights, rotating weights, and surface torque, and how these measurements are taken consistently and interpreted accurately. Second, interpret broomstick plots, which compare measured loads to modelled values. These plots are powerful diagnostic tools, allowing us to identify poor hole cleaning, cuttings bed development, or excessive drag during casing runs. Third, evaluate how drill string design influences torque and drag. Each section of the string plays a specific role, and by adjusting placement, weight, and stiffness, we can minimize drag and improve load transfer. Finally, explain the mechanisms used to reduce torque and drag. This includes mechanical approaches like rotary steerable systems and torque subs, as well as chemical methods such as lubricating additives. Together, these techniques form a comprehensive toolkit for optimizing drilling performance in challenging well trajectories. Now, let's examine the key parameters that must be monitored to effectively track torque and drag behavior during drilling operations. In practice, 4 main measurements are required. The first group are hook loads, which are captured during pickup, slack-off, and rotation. Pickup weights are measured by lifting the string 15 to 20 feet at constant speed, providing a value that includes both string weight and drag. Slack-off weights are measured by lowering the string under controlled movement, where drag reduces the apparent hook load. Finally, rotating off-bottom hook loads, measured 5 to 6 feet above bottom, help establish baseline drag while minimizing bit interaction. The second parameter is torque, recorded at surface. Off-bottom torque values, measured at a steady rotary speed, provide an indicator of frictional resistance along the string without the additional influence of bit-cutting loads. These measurements, when taken consistently, provide the foundation for torque and drag analysis. By comparing them against modelled predictions, we can identify deviations that may indicate poor hole cleaning, cuttings accumulation, or tight spots. Accurate monitoring ensures that engineers can respond proactively, adjusting drilling practices, fluid properties, or string design before problems escalate into stuck pipe or lost time. Torque and drag monitoring is such a critical part of drilling operations. At its core, monitoring provides a continuous assessment of hole condition and deterioration. By tracking pickup and slack-off weights, we can detect early signs of increased drag that may signal developing tight spots, cuttings accumulation, or borehole instability. Another major benefit is evaluating hole cleaning efficiency. Poorly cleaned wells allow cuttings to settle and form beds, which dramatically increase drag. Torque and drag trends provide a direct measure of how well the mud system and circulation practices are keeping the wellbore clean. Monitoring also helps determine the limitations of equipment and maximum achievable depths. As torque and drag rise, the effective reach of the drill string is reduced. Identifying these limits allows engineers to decide whether trajectory modifications, mechanical aids, or lubrication are required. Additional insights include the effects of mud lubricity, mud weight, and property changes on drag performance. By comparing data across different drilling fluids and well sections, we build a friction factor database that strengthens future well planning. Ultimately, monitoring is about prevention, detecting and understanding problems before they stop progress, whether running casing, liners, or drilling ahead. When should torque and drag measurements should be taken? The key principle is consistency. Data must be captured at critical operational stages so that trends can be identified and compared. Measurements should be recorded at every connection and while tripping in or out of the hole. These are routine moments when the string is already being moved, making them ideal for collecting baseline pickup and slack-off data. Monitoring is also essential prior to drilling out or re-entering open hole, particularly after casing or a sidetrack. This ensures any drag increase is detected before significant progress is made. Other key checkpoints include after major inclination or azimuth changes, where side forces increase and drag behavior shifts. Wiper trips designed to clean the hole should always be bracketed by measurements to confirm their effectiveness. Torque and drag readings should also be taken before and after circulating bottoms up or pumping sweeps, as these operations directly affect hole cleaning. Finally, monitoring is necessary after mud type changes or major mud property adjustments, as lubricity directly impacts friction. In casing runs, drag values should be checked every 3 to 5 joints, ensuring no unexpected restrictions compromise running operations. How do we take torque and drag measurements? They should be reliable and repeatable. Consistency is the most important factor. If procedures vary, the results cannot be meaningfully compared against previous data or model predictions. First, when moving the drill string, it should be done at a constant speed. Pick-up and slack-off movements should each be 15 to 20 feet in length, as short movements can be distorted by elastic stretch or mechanical lag. Second, use the least affected, steady weight indicator reading. Transient fluctuations from rig equipment or driller handling must be avoided. Stable readings provide the most accurate measure of drag forces. Third, before making a connection, the pump should be turned off. Take pick-up and slack-off weights in non-circulating conditions, then repeat with circulation if required. This allows us to distinguish between hydraulic lift effects and true drag. Additionally, circulating readings should always be taken at the same flow rate within a hole section. This prevents variations in hydraulic lift from being misinterpreted as drag changes. Finally, during trips, only pick-up weights are required when pulling out, and slack-off weights when running in. This ensures efficiency while still collecting meaningful data. With the introduction of software to track and monitor, and more recently, the incorporation of automation into rig equipment, this process is becoming more reliable and is now performed as a routine operation. Continuing the discussion on how torque and drag data should be acquired and applied. Beyond basic pickup and slack-off procedures, we also use circulating measurements to estimate the maximum achievable depth while drilling. By comparing drag trends during circulation, engineers can determine if the wellbore condition will support further progression without intervention. For casing and liner runs, the same principles apply. Slack-off weights should be recorded while running casing or liner, as this is when drag forces can become a limiting factor. Excessive drag at this stage can prevent casing from reaching target depth, so careful monitoring is essential. Pumps on readings are also valuable because they help quantify the combined effects of friction and hydraulic lift. This is especially important in extended reach wells, where cuttings, transport and hole cleaning efficiency strongly influence drag. Here, we introduce the broomstick plot, which is one of the most effective ways to evaluate torque and drag behavior. The graph plots hook load versus measured depth, giving us 3 main curves: pick-up weight, slack-off weight, and rotating weight. The pick-up weight curve represents the hook load measured while lifting the string. It includes both the string's free weight and drag effects. The slack-off weight curve shows hook load during downward movement, where drag reduces apparent weight. The rotating weight curve falls between the two, representing conditions when the pipe is rotated while moving, which typically reduces friction. Overlaying these measured curves are modelled or planned dotted lines, generated from torque and drag simulations using assumed friction factors. These serve as the baseline for comparison. If the measured lines align with the modelled curves, it indicates the well is behaving as expected and hole conditions are good. When divergence occurs, as in this example, it signals abnormal conditions. Here, the actual measured pickup line deviates above the planned curve, while slack-off data also diverges. This divergence is diagnostic of poor hole cleaning, especially in the tangent section, where cuttings beds increase drag and reduce effective hole diameter. Here we can see 2 broomstick plots, both representing casing running operations but under very different conditions. By comparing them side by side, we can see what distinguishes a good casing run from a problematic one. Starting with the left-hand graph, which is an example of a good case, the plot shows hook load versus measured depth with the expected modelled lines, dotted for pickup, slack off and rotating. The actual measured slack off during the run closely trends with the model. The pickup curve consistently lies above the slack off curve, exactly as expected. Notably, the separation between the pickup and slack off lines remains stable across depth, reflecting consistent friction behavior. This tells us the hole is well cleaned, friction factors match the model assumptions, and casing is running smoothly to bottom with no abnormal restrictions. Now turning to the right-hand graph, which is an example of a bad case, here, divergence is immediately evident. The measured pickup line rises above the modelled prediction as depth increases, while the slack-off line falls below its expected position. The gap between measured and planned curves widens with depth, a classic indicator of excessive drag. This behaviour points to deteriorating hole conditions, most likely cuttings, bed development, partial pack-off, or poor mud lubricity. As casing is run deeper, these effects intensify, increasing the risk of casing getting stuck or failing to reach target depth. By contrasting these two plots, we see how broomstick analysis provides real-time diagnostics. In the good case, casing can be confidently advanced. In the bad case, the data clearly signals the need for remedial action, such as wiper trips, increased circulation, or lubrication additives before proceeding further. If we look at the well trajectory, it is broken into 6 distinct sections, each with specific drill string design requirements. The key message here is that as the well is drilled, the same pipe passes through multiple sections, so string design must account for its changing role along the trajectory. Section 1. Toe of the well. This is where the final reservoir target is achieved. The drill string here must provide precise directional control while minimizing torque and drag. Section 2. Horizontal section. This section requires efficient weight transfer to the bit in a high-friction environment. The string here must be stiff yet lightweight to reduce buckling and drag while maximizing hole cleaning. Section 3. Landing. The transition from the build to the tangent. This zone requires high buckling resistance as forces peak when the wellbore flattens. Section 4. Build-up section. This is the curved section transitioning from vertical to deviated. String design must be stiff enough to transfer weight, but overly heavy components such as collars here will eventually end up in the horizontal, where they cause weight transfer problems and increase stuck pipe risk. Section 5. Vertical section. Prior to kickoff, this is the straight section of well. As drilling progresses, the pipe in this zone eventually spans into sections 4 and 3, meaning its design influences multiple phases of the well. Section 6. String to surface. The upper part of the drill string supports the full system. It requires high tensile and torsional capacity to withstand loads transferred from deeper sections. The important lesson is that drill string design cannot be static. Engineers must anticipate where components will end up later in the well, ensuring that weight, stiffness, and buckling resistance remain balanced throughout drilling. Now let's look at practical methods for managing torque and drag, divided into 3 categories: torque reduction, well path considerations, and drag optimization. Starting with torque reduction. One of the strongest influences on torque is the well trajectory itself. Designing smoother profiles with minimal doglegs reduces contact forces and friction. Next, the distinction between cased hole and open hole is important. Torque is usually higher in open hole due to roughness and instability, so lining critical intervals helps. Mud lubricity can be improved with lubricating beads or additives, lowering the effective friction factor. Similarly, lost circulation materials, LCM, and torque-reducing chemicals may be added to reduce wall contact resistance. Finally, torque-reducing subs and drill pipe protectors can mechanically shield the string from abrasive contact. Keep in mind, whatever you physically add to the string has a pressure drop and may cause hydraulic limitations. Also, they make break and become junk which have to be fished. Next, well path considerations. Trajectory design is central. Gentle curvature minimize tortuosity, and smooth build sections reduce torque and drag. The bottom hole assembly BHA also plays a critical role, as steerable rotary systems can optimize torque response. Choosing an optimum profile that balances geological targets with mechanical efficiency is one of the most powerful design levers available. Finally, drag optimization. Here the focus is on axial drag. The well profile itself determines side forces, so smoother paths minimize drag. Mud lubricity is again vital, reducing sliding resistance. Drill pipe protectors reduce casing wear and distribute contact forces. Engineers must also consider buckling effects, since buckled pipe greatly increases drag. Proper weight distribution across the string helps maintain stability. Other strategies include maintaining effective hole cleaning, using downhole motors to reduce surface torque demand, and applying continuous rotation with steerable rotary systems to prevent static friction buildup. Together, these practices ensure that torque and drag are not just monitored, but actively controlled through both design and operational choices. This slide shows examples of mechanical torque and drag reduction tools divided into cased hole on the left and open hole on the right. Starting with the cased hole tools, drill pipe protectors, shown in orange, rubber or polymer sleeves that centralize the pipe inside casing, reducing metal-to-metal contact and minimizing casing wear. They are normally placed at intervals along the drill pipe in the case section. Either side are stop collars to prevent them from moving axially along the pipe. This increases the hydraulic pressure required, which may reduce the flow rate due to pressure restrictions. Also, the rubber elements can be damaged and fall off, causing a fishing problem and a potential stuck pipe issue. Rotating protectors/subs. These rotate with the drill string, reducing torque by lowering friction against the casing. They are placed in high contact areas where side forces are greatest. Centralizers, mechanical devices fitted around the casing to keep it centered with rollers on them, reduce friction. Now the open hole tools. Stabilized subs, black, blue and gold. Placed in the BHA, they are used to stir up the cuttings, improving the hole cleaning efficiency and therefore reducing the torque and drag. Non-rotating drill pipe protectors, NRDs, blue with gold sleeve, fixed sleeves that allow the string to rotate inside while the sleeve remains stationary, reducing torque. The stabilizer in red also has a non-rotating element with rollers that reduce drag. These tools are strategically positioned where drag and side forces peak, ensuring smoother drilling and reduced torque demand. Mud additive lubricants are available in two types, liquid or beads. The beads are generally made from glass or polymer materials. They are designed to reduce friction between the formation and downhole tools. Lubricant has a life expectancy of a few days and works very well before it breaks down. Beads are a mud company's dream. You put them in at one end of the circulatory system and they come out with the cuttings at the other end of the system, only to be replaced so that the operation can be repeated. Now let's look at the parameters to monitor for improved torque and drag. Looking at string design, first, placing the heaviest drill string components in the vertical hole section helps ensure that weight is supported where drag forces are lowest. This reduces the risk of heavy collars ending up in the horizontal section where they can create buckling and weight transfer issues. Second, minimizing tortuosity in doglegs through careful well path planning reduces side forces. Every bend increases wall contact, so optimized trajectories directly lower drag. Third, using a rotary steerable system, RSS, can reduce drag by keeping the string in continuous rotation while steering. This eliminates static friction associated with slide drilling. Fourth, torque-reducing subs should be strategically placed where side forces peak, such as in high-angle build or tangent sections. These subs act as mechanical aids to reduce wall contact. Fifth, ensuring proper hole cleaning is fundamental. Even the best designed string cannot overcome excessive cuttings beds. Finally, adding lubricants provides temporary reductions in friction, useful in casing runs or extended horizontals. While not permanent solutions, they can extend operational reach and reduce stuck pipe risk when carefully applied. Here are general guidelines for optimizing torque and drag. First, run torque and drag simulations at several key depths, not only at TD. This helps track hole cleaning and predict drag progression. Limiting analysis to total depth can mask intermediate issues, such as cuttings beds forming mid-well. Second, remember that torque and drag are caused by lateral forces and friction in the wellbore. Lateral forces increase with inclination, doglegs, and borehole roughness, while friction is influenced by formation, contact, and mud lubricity. Recognizing both contributions is essential when diagnosing problems. Third, the BHA should be designed to achieve the required build or turn tendencies with maximum rotary drilling. Sliding increases drag and torque unpredictability, so designs that minimize sliding improve efficiency and hole condition. Fourth, bit torque should be continuously monitored. Bit torque is a key indicator of drilling efficiency and formation response. A stable torque trend suggests good conditions, whereas spikes may indicate harder stringers, poor hole cleaning, or impending dysfunctions like stick slip. Taken together, these guidelines highlight that torque and drag optimization is not a single adjustment, but a continuous process involving predictive modeling, efficient BHA design, and real-time monitoring to ensure safe and efficient drilling progress. Let's review what we have covered in this submodule on torque and drag. We began with the parameters to monitor. You learned that pickup, slack-off, rotating weights, and surface torque provide the baseline data for tracking drag and detecting borehole problems. We then explained why, when, and how monitoring should be performed. Monitoring ensures early identification of deteriorating hole conditions, confirms hole cleaning efficiency, and provides data on equipment limitations. We emphasized that measurements must be taken consistently at every connection after inclination changes, before casing runs, and using steady movement at constant speed. Next, we introduced the broomstick plot, showing how measured hook loads compare to modeled values. We interpreted examples of poor hole cleaning and casing running, demonstrating how divergence between actual and planned curves provides immediate diagnostic insight. We then covered drill string design, breaking the well trajectory into 6 sections and discussing the function, desired characteristics, and design considerations for each. The key takeaway was that string components move through multiple sections as the well deepens, so placement must anticipate future conditions. Finally, we reviewed torque and drag reduction strategies, including mechanical tools, mud additives, and operational practices for optimization. Thank you for your attention throughout this module. We've completed Submodule 3, the final part of our torque and drag series. You should now be confident in monitoring, interpreting, and managing torque and drag, applying both mechanical and operational strategies to optimize drilling performance safely and effectively. Please progress to the quiz.